All right, we're going to take a look at 3.7 and 3.8 in the book. Not titled Determining the Formula of a Compound, but we're actually now going to look at chemical changes and the reactions that we use and that we write in order to describe chemical changes. Remember now, chemical changes involve the reorganization of atoms. Mass is never lost. If you start with 20 grams of reactant, that's the stuff on the left side of the arrow, at the end of the day, you need to have 20 grams of product. And now, sometimes it's not easy to capture that 20 grams of product. Maybe some of it is released as a gas, or to scrape every single piece of solid out of a beaker might be difficult to do. But mass is never lost. That's the law of conservation of mass. It's got to go somewhere. So, chemical equations are what we use to illustrate these changes. We've done these before. We did them in general chemistry class. And these chemical changes are often called chemical reactions. And it's these equations that we use to illustrate them. Now, when I talk about reactions, oftentimes I'm going to abbreviate that with the three letters RXN, just for brevity. Let's take a look at a sample chemical reaction. This is natural gas, CH4. Methane is also known as natural gas. It's the stuff that comes out of our spigots to light our Bunsen burners. And if you live in town here, that's what you use to heat your home, most likely. But when we burn it, it actually burns with the aid of two oxygen molecules. Notice I say molecules and not atoms because oxygen is diatomic. So that means that oxygen's never alone. It's always got a buddy. Well, in this case, the CH4 bonds with those two oxygen molecules to produce two products, one being carbon dioxide and the other one being water. And you'll notice that there's actually two water molecules. And if you were diligent and you went along and you tried to count each one of these spheres that are located on the board, you'd notice that they equal out. The left side and the right side equal out. 1, 2, 3, 4 here on the left side, and 1, 2, 3, 4 here on the right side for the reds. There's a single carbon there and a single carbon on the right side there. And then the whites, there's actually one hidden here on the left side. 1, 2, 3, there's one right back there, 4. And then 1, 2, 3, 4. So this is a balanced chemical equation, something that's very useful for us. What does a balanced chemical equation tell us? Let's go back to the one that we just saw. All right, what do we know about this? Well, first of all, we know that we've got a couple of reactants, we've got a couple of products. What are reactants? Well, our reactants are methane and oxygen. So I'm going to rewrite the chemical reaction right here. CO2 plus 2H2O. Okay, what else do we know about this? Well, we actually know that... Sorry about that, I stopped the recording for a second. We also know that this reaction occurs only if one molecule of CH4 combines with two molecules of O2, and that will give us every single time one molecule of CO2 and two molecules of H2O. Right? But we know that we never really deal with just a single molecule of methane or two molecules of oxygen. It's always bigger than that. So what do you think is more useful for us? Now, hopefully you said the mole, right? We can also write this that 1 mole of CH4 reacts with 1 mole of CO2. Be careful, mole and molecule, totally different. And that gives us 1 mole of CO2 plus 2 moles of H2O. Okay? Think about mass-wise here. What's the molar mass of CH4? Well, you've got 4 hydrogens and 1 carbon, so that comes out to 16.04 grams per mole. And there's 1 mole of that. Okay. You have 2 moles of O2 over here. I don't know why I said 1 mole. That's 2 moles of just O2. Okay. So what is that? You got 16 times 2 for an O2, and then twice that, so you got 64. Plus 64 grams per mole here. How about on the other side? You've got CO2, that's 44.01 grams per mole. Plus H2O, which is 18.02 times 2, it's 36.04. And go add all those up, and what you should see is kind of a mathematical equation. 16.04 plus 64 equals 44.01 plus 36.04. And I know they're off by a little bit, but there's some rounding there, right? Okay, so we can also say mass to mass, right? Now, if we want to get to the big gaudy numbers, we could say that there's 6.022 times 10 to the 20th Avogadro's number times 10 to the 23rd atoms or molecules of CH4. So Avogadro's number of CH4 plus 2 Avogadro's number of O2 yields Avogadro's number of CO2 plus 2 Avogadro's number of H2O. Right, if we were to count each individual molecule, which we typically don't do. Now, which ones are we going to be most concerned with, and are we going to work most with? This guy and this guy. Okay, the other three are fun to talk about, or the other, actually, this top one too with reaction. The other two are fun to talk about, molecules and Avogadro's number, but they're just not all that useful to us. Okay, so last slide, and just to recap here, the balanced equation represents an overall ratio of reactants and products. Not what actually happens during a reaction. It doesn't show you how the bonds of the reactants break and how they transform and move around. It just shows you the overall ratio of reactants and products. We'll get to that bond breakage and the moving of the atoms a little bit later. We need to use coefficients, and the coefficients are the numbers that go in front of each molecule to balance the equation. We need to use the coefficients in the balanced equation to decide the amount of each reactant that is used and the amount of each product that is formed. So balancing a chemical equation doesn't just adhere us to the law of conservation of mass. It also allows us to understand how much reactant do we need, and at the end of the day, how much product will we produce. And those, as you probably can think, are two pretty important questions to understand. Okay, that's it.